This afternoon's lecture, this evening's lecture, is about a Polish encryption machine called LACIDA. Before I talk too much about LACIDA, though, I'm going to explain for the benefit of people who don't know so much about the encryption systems that were used during the war, about Enigma, and then the lecture continues with explaining some of the differences between LACIDA and Enigma. So first of all, let's start with an introduction to Enigma. Now, what is an Enigma machine anyway? And the answer is, it's not that simple of a question to answer. And there is this tree of Enigma machines, and this is a slightly out of date tree. As you can see, it's dated 2009. And since this was produced, further Enigma type machines have been discovered or worked out, determined to have existed. There is, for example, this one, which looks nothing like any of the Enigma machines you see in movies. It has a printer on the top, it has handles on the side for turning the wheels and so on. There's this one, which looks a bit like the ones you see in the movies. That it has 4 wheels, but it only has a numeric keyboard, so it's primarily used for encrypting series of numbers. This is the standard 3-rotor Enigma, which I'm going to go into in more detail in due course. There's also a 4-rotor Enigma, a 4-wheel Enigma. You can see the 4 wheels at the top. This is a rather special machine, which is in the Institut Józefa Piłsudskiego for Lodinier. It's a French-made an Enigma, made to Polish designs. There's only 4 of these known to exist, and 2 of them, in fact, is not known where they are these days. This one's in London. There's another one somewhere in Paris. So I'm going to proceed with standard 3-rotor Enigmas. Now this will probably be a bit boring for many of you, but I'm going to explain a bit about encryption anyway to start with. There's a cipher known as the Caesar cipher. And let's just consider the case where I've got although it was originally used in Latin, I'm going to use an English example, a very important message which must be kept secret. And you just write it out the alphabet A to Z, and underneath it you write on the alphabet A to Z plus 5. So A becomes F, B becomes G, C becomes H, all the way down to Z becoming E. At the end of the alphabet on the lower line, you wrap around the beginning of the alphabet. And then you can just convert my very important message into FAJWD, NRUTW, and so on. And it's tradition in ciphering applications to break up the words, or to take out the spaces in the words and then separate all the remaining letters into 4-letter groups or 5-letter groups. Now, it's really easy to decrypt this because if you know it's a Caesar cipher, you can just work your way testing one alphabet after another. And eventually, when you've got back to having a separation of 5, you end up with the original very important message. Excuse me. You've lost the letter spacing, but you can, if you can read the language, you can then recreate the message. Now, another way of solving this is to say, let's count the letters. So in the encrypted message, there's 1A, 1B, 1D, 3 Fs, a G, 2 H's, and so on. Now, English has a biased letter frequency, like most world languages, and the letter E is well known to be the most common letter in the in standard English text, followed by the letter T, and then followed by other letters in an order which can vary a bit. But if we just look at the encrypted message, you can see there's a lot of J's and slightly fewer Y's. So we can take a guess that J actually represents E and Y actually represents T. So I've now regained, if I can now do the subtraction J minus E and equate that to Y minus T to get the 5, which was the key that I used in the first place to do the encryption. I can make this more complicated now by having key of 5 for the first letter and key of 6 for the second letter and key of 7 for the third letter and so on. And if I encrypt like that, then the distribution, the bumpiness, if you like, in having counted all the letters has been somewhat reduced. And now you can see there's 4 C's and 4 G's, there's 3 M's and 3 Y's, and you can't really work out which the most common letter in that sequence is to reverse engineer to get back to the original encrypted message. Enigma takes this one step further yet. I'm going to go through the various parts of an Enigma. There's a plate in the lid, which, as you can clearly see, is primarily just cleaning instructions. Although along the bottom there is a representation of the alphabet, letters, and under that numbers. And that's to allow you to have Enigma wheels, some of which are enumerated in letters and some of which are enumerated in actual numbers. So you can swap between letters and numbers without having to count on your fingers. Now, this is a little simulation which some colleagues of mine have created. And I'm going to demonstrate how the letter A gets encrypted to H at this particular setting of the wheels. So the first thing I do is I hit the A key. And that causes the wheels to turn. The rightmost rotor always turns. The leftmost, the middle rotor turns 1 in 26 times, and the leftmost rotor turns 1 in 26 steps of the middle rotor. So you end up with 16,576 positions, approximately. There's a quirk in the Enigma which actually means that that number is not actually quite as large as 16,576, but that's not particularly relevant to this explanation. So the wheels have, 1 or 2 or 3 of the wheels have turned, and current now starts to flow from the battery at the right through the switch, which has been flipped by pressing the key, and into a plug board on the front. The current then flows through the plug board, and it's now flowed from the A to the M and continues up into the rotors. It goes through the rotors, and then it bounces off, so as to speak, the very leftmost wheel, which is actually, generally speaking, static, called a reflector. It goes through the reflector and then reverses back through the wheels. Back into the plug board on the front, and then it lights up the H. Now, the next time, if I were to do this again, because at least one of the wheels has turned, then the current path will be different. So it will be some letter, probably not H, but it's a reasonable chance that it could be an H again. The one thing it can never be is an A, however. Now, this is an Enigma simulator, which I'm just going to go through a few of the features on. I started in this example with the 3 wheels of the 3-rotor Enigma set to the letters A. After I've encrypted 4 letters, AA, AA, the wheels are now standing at AAE. Excuse me. Each Enigma rotor has what's called a ring. Effectively, the rotors are built in 2 parts. So there's the wiring matrix of the rotor inside, and then a ring with the letters of the alphabet written on it, which is a separate component. And it can be rotated relative to the wiring matrix. Now, the 26 positions of the rotors can be equated to the 26 positions of the ring setting. So a rotor position of B with a ring setting of B is equivalent to a first approximation to a rotor position of A with a ring setting of A. Although because there's notches on the rotors which determine when each rotor steps the next rotor, you have a change in the turnover points. So if I have encrypted a long test message using the wheel positions of JFK and the ring settings of EWR, and then decrypt it, then obviously at the same settings, I get the original message back again. If I step both the wheel positions by one manually and the ring settings by one manually, then when I decrypt, there's a gap here because I've changed the stepping position. If I add another one to each of these positions, there's now a 2-character wide gap, and then a 3-character wide gap for the next step. Now, the rotors are generally enumerated in Roman letters, Roman numbers, I should say. And the Enigma machine can have the wheels taken out and have the wheels put back in any order. So if in the default case you have 3 possible rotors, then you have 6 ways of putting the wheels in. In this example, I have rotor 1 on the left, rotor 2 in the middle, and rotor 3 on the right. Finally, the very leftmost non-turning rotor is selected from one of 2 traditionally options. This is the reflector I mentioned earlier. Typically, they come as A or B or C. A wasn't used very long. B and C are the ones more often used. Now, coding sheets like this are used to show the are distributed to instruct the operator how to set the machine up for a given day. So for the 29th of November, which is today, then the reflector, represented by UKW, Umkehrwalzer, is the B reflector. The Walzenlager, the order in which the wheels are put in. And this is an example with 8 possible wheels. So you have rotor 3 on the left, 4 in the middle, 5 on the right. The rings on those wheels are set to 26, 19, and 16. And the plug board on the front, which I'm going to go into a little more detail shortly, are set with A connected to C, F connected to L, H connected to V. And those are reciprocal connections. So not only is A connected to C, but C is connected to A. This is an example of the plug board on the front. You can see each letter is represented by 2 sockets. So when the cable you can see that's plugged into the A interface is connected to the M on the right, and you actually have the top pin in the A plug connected to the bottom pin in the M plug, and the bottom pin in the A plug connected to the upper pin of the M plug. And the effect of that is applies both during the keyboard, the processing of the keyboard data, and the processing of the lamp board data. If I just would have typed AAAA on a machine with no plugs, then the encryption would be BDZG. Because I've connected B to G and P to Z, then the encryption becomes GDPB. Right, I'm now going to introduce a little bit of math. I'm told that every mathematical formula you put in a presentation causes at least one person to drop out, but I hope this won't happen here. There's a number called the index of coincidence. and I'm not going to go too much into this, but it's a handy number for working out whether or not you're looking at a human language, and to some degree you can work out which human language you're looking at the text of. So you can tell the difference between, by doing some math on all the letters in the text, you can tell if you're looking at German, you're looking at English, if you're looking at some other language that has 26 letters in its alphabet. And I appreciate German doesn't technically have 26 letters in its alphabet, but I hope you get the point. And you can also tell if you're looking at a random letter stream by looking at the values produced by this algorithm. And if you're looking at a random bit stream, then you end up with an index coincidence value of 0.037 recurring, which is roughly 1 in 26, which of course is roughly 1 in the number of letters in the alphabet. So if I input the letters A to Z multiple times and into an Enigma, and I get a text stream IDD, RPO, and Q, and so on, then the index coincidence of both A to Z repeated multiple times and the encryption of A to Z repeated multiple times is both about 0.37037 recurring. That's just a repeat of the previous slide. We can skip that. When I was studying this index coincidence, I did select some texts, and this one came from the New York Times. And if I do the index coincidence calculations on that, the plain text, rats or not, transit chief opposes ban on eating in the New York subways, I end up with an index coincidence value of 0.064. If I encrypt that on an Enigma, then again, I get a value fairly close to 0.037. This is a repeat of another text, which I'm not going to belabor. Now, when you're coming to decrypt Enigma texts, or indeed any encryption system, there are two approaches. There's the so-called known plain text attack, in which you know or are prepared to take a guess part of the original message. And there's a ciphertext attack, in which you have no clue as to what the original message said in any part of it. And I'm going to cover that first, because, as you may know, Polish mathematician engineers managed to break Enigma even before the war started. And here we have a gentleman who goes by the name of Marian Rejewski, who proudly says, "Skrakowałem Enigmę," I broke Enigma. In fact, he probably wouldn't have said that, because I understand he was a fairly modest gentleman. He was born in 1905, died in 1980, a Polish mathematician and cryptologist, and in the year 1932 broke the Enigma cipher, along with two colleagues, Henryk Zygalski and Jerzy Różycki. They did a lot of this work in the city of Poznan, which is roughly halfway between Berlin and Warsaw. There is a memorial to them outside the Zamek Poznański, the castle of Poznan, and it shows their three names. There are people, including myself, who've been trying to work out if any of the numbers have any significance. And the only numbers we've managed to work out any significance are immediately above, in this example, you see, immediately above the word Henrik, you see 15071908, and that's his birth date. And underneath the word Zygalski, you will see 30/08/1978, which is the date of the day of his death. This is me standing next to this memorial, and I haven't put this in so you can look at me, but to look at the building behind, which is a building in which people are going to be building an Enigma I've been told not to call it a museum, but an Enigma explication center, shall we say. Now, the Poles created a number of methodologies for cracking Enigma, as well as creating the LACIDA machine, which I'm going to get onto shortly. I'd like to just mention a concept called depths. And there are two sorts of depths, in effect: encrypting the same message using different keys and encrypting two different messages using the same key, the same one key. And that second depth type resulted in the British break of the Schlüsselzusatz 42, the SZ42 encryption system, and the subsequent construction of machines such as Colossus. But that, as they say, is another story. Enigma operators introduced depths of type 1 when they were sending the wheel settings that they'd use to send a particular message, encrypting them twice sequentially. So they had a 3-letter key. They've said, I've set my wheels to XYZ, for example, and I'm going to tell the receiving end how I've set my wheels, and I do that by encrypting XYZ on my Enigma, and I type in XYZ, XYZ. So I've typed the same 3-letter message or message fragment using different keys, using sequential keys. And this gives rise to a number of problems, and which I'm not going to go into in this lecture because that's a whole hour of more stuff. But you can, given sufficient messages, you can determine the so-called cyclic properties of Enigma. And using these cyclic properties, various machines or systems were created, the simplest of which is the Płachta-Zygalski-Jego, the Zygalski sheets. Marian Rejewski did explain that when these sheets were superposed and moved appropriately, then eventually you might get an answer as to how the machine had been sent up for a sufficient number of messages. As you can see, it's a bit vague. There remained a signal aperture, probably corresponding to the right case, that is, to the solution. I tried printing out some Zygalski sheets and making the work myself, and I found it became rather a mess once you had more than 2 or 3 stacked on top of them. So, in fact, I wrote some software to simulate Zygalski sheets, and I find, happily, that the system works. Jerzy Ruzicki, one of Marian Rejewski's colleagues, created a system called the Metoda Cygara, which means clock method in Polish. And it was subsequently reinvented, either independently or not, in Bletchley Park, where it was called Banbarismus. And it allows you to compare 2 messages, 2 encrypted messages, to see if one message was encrypted at a nearby start position to another message. Marian Rejewski created a machine which is basically 2 Enigma machines linked together, called the cyclometer. As you do, I have one of these myself as well. This is a software implementation, but it runs with the same collection of switches and lights that this totally hardware machine used. The Poles also created a machine called a bomba, which is not to be confused with, although it inspired the Turing-Welshman bombe that we have at the National Museum of Computing. And as it happens, I have one of those as well. Now, another attack is the known plaintext attack. Now, as I mentioned earlier, the Enigma machine cannot encrypt any letter to the same letter. So you can, if you've got an encrypted message and you think you know what the plaintext message was, then you can do a thing with a slide rule like this to determine or to exclude certain starting positions of the message, certain matching positions between the plain text and the encrypted text. And then you can take the encrypted message, line it up against the guessed at, the crib plain text, and you can create this menu, as it's called, which always looks to me like a bit of organic chemistry. And then you run it on a machine like this. This, as far as I know, is a mock-up from a film, and it looks like the lady standing to the left is also not actually real. That's what it looks like to me. There is a simulator for this, which I encourage anybody who might want to go and have a play with. But this is not really the topic of today's talk. There's a 4-rotor bomb as well for the one of the Enigma machines, which was used, which had 4 wheels rather than the standard 3 that I've been talking about. Now, there are other Enigma-like machines, one of which is this. It's Russian. It's called a fialka in both Russian and English, or a fiołek po polsku in Polish. Instead of having 3 wheels, it has 10. It has a reflector, but it has what they call a magic circuit, what modern people are calling a magic circuit, which allows letters to encrypt to themselves. Instead of having the plug board, it has a punched card in the side to program the activity of changing one letter into another. It has a very interesting keyboard with 4 alphabets on it, and it has a connector on the side for plugging in teleprinters and so on, transmitters and so on. A Swiss machine called the Enigma. This one's actually post-World War II, but it works similarly to Enigma. It has, in this case, it has 10 things that can turn. I'm not going to call them rotors because technically they are pairs of rotors and rings which are interconnected. I think this one's probably my favorite after the LACIDA. It's a Japanese attempt at producing an Enigma. And it has 42 characters, which you select between using the shift keys bottom left. And this is a simulation that I wrote recently. The Type X is a British machine similar to Enigma. It's sufficiently similar to Enigma that it can be wired to behave like an Enigma. And there's a Hebrew version of the Enigma as well, which was created by taking captured German Enigmas and just changing all the alphabetization to work in Hebrew. Now we come to LACIDA, and now we can see what the differences might be. It is named after 3 people who are, or possibly 4 people who were involved in its design, involved in its creation. We have Guido Langer, we have Maximilian Cienski, and we have Ludomir Danielewicz, or possibly his brother, Leonard Danielewicz. But unfortunately, there doesn't seem to be a photograph of this gentleman. Now, it's actually, this particular encryption system is not purpose-built to be an encryption machine, because what you have is an electric typewriter at the back and a box full of wheels on the front. And there's a cable that runs from the electric typewriter into the box, and the data goes in and comes out. The data comes in from the keyboard and comes out on the printer. This is a Polish version of the same picture. And what it shows is, slightly better than the previous one, is 3 wheels visible through a box, the lid of the box. But as it happens, there are 6 wheels in total, and 3 of them are set by opening the lid, turning them, and then closing the lid again. So 3 of them are set for a day, and 3 of them are set for each message. Now, it's somewhat unusual in its design, because the wheels have different sizes. So some of the wheels have 24 positions, unlike Enigma, which has 26 on all of its wheels. Some of the wheels have 31 positions. Some of them have 35 positions. And some of them actually have 24 positions on one side and 31 on the other. And this one here has 31 on one side and 35 on the other. Now, the keyboard is also, the number of keys on the keyboard varies depending on whether you are encrypting or decrypting. During encryption, only the keys which are outside of this dotted line are active. So during encryption, you have W through U plus O, A through K, and P through L. And the output is 35 characters from this 24 keys. And that's the 26 letters of the Latin alphabet, followed by some numbers. Now, when I say the 26 letters and some numbers, in fact, one number is missing because it can only encrypt from 1 to 9 or to 1 to 9. And in decryption mode, you have all the keys available, 1 to 9, and all the letters from A to Z. And if you wanted to encrypt an 0, then you would use the letter O. Now let's compare it with Enigma, 3-rotor Enigma. 3-rotor Enigma has 3 rotors used twice because the current flows first through the rotors from right to left, bounces off the reflector, and then back through the rotors from left to right. So you have 3 wheels, but they're used twice each. LACIDA has 6 wheels. There's no reflector on LACIDA. So it has 6 wheels, single direction. Enigma has reflector, LACIDA has no reflector, as I said. That means that no letter can encrypt to itself, which means that this slide rule thing, if you're trying to match up cribs with enciphered messages, isn't going to work for you if you are trying to decrypt LACIDA messages. Enigma wheels, 3 of them, there's 26 possible settings, giving you a total of 17,576 possible starting positions. LACIDA wheels have variously 24, 31, and 35 possible settings, giving you around 1,000 million start positions, which is an improvement of approximately 56,000. But LACIDA has no plug board. So actually, the 56,000 improvement that you've gained by having 6 wheels with these various numbers of settings is only equivalent to around 2 cables and a bit that you get with Enigma. Enigma was used with typically 10 cables, and that gives you 150 million possible combinations of the cables. You have to have, because of the setup of the design of the machine, you have to have an explicit encipher decipher switch. And this is generally speaking, it's deprecated to have explicit encipher decipher modes because people will sometimes get them wrong and will encrypt in decipher mode or decrypt in encipher mode, or attempt to. The 3-rotor Enigmas can have its rotors if it only has 3 to choose from in one of 6 sequences. The LACIDA wheels are fixed, so there's no variation in the wheel order. So just to summarize, the current flow, in this case, we have 26 coming in to the rightmost rotor. It goes from through 3 wheels, which are 26 on each side, through the reflector, which doesn't turn, 26 in, 26 out, 3 more wheels, and then 26 positions out. Now, LACIDA has entry in one direction, left to right, and encryption in one direction, left to right, and decryption, right to left. 3 of the wheels turn during encryption. They're the ones that you can adjust on the outside of the box. 3 of the wheels, the ones in brackets, are fixed and are set for the day. That means that pretty much all of this data in the Enigma coding sheet has become irrelevant, because about the only thing you can change is the equivalent of the Ringstellen, which you can consider to be the analog of the fixed wheels settings for the day. But there's no reflector. The Walzenlager is fixed because you can't take the wheels out and reorganize them. There's no Steckerverbindungen. There's no plug board. In summer 41, Polish intelligence chiefs decided that their cryptologists, Rejewski, Rzycki, Zygalski, should try and crack LACIDA. They decrypted some LACIDA messages in less than 2 hours, and the resultant consternation was somewhat enormous. And LACIDA didn't actually get used a lot after that. It was a nice try, but there you are. Now this is my simulation, which I will run later on. I've just typed in rather boringly the text hello here, and you can see it is encrypted to JPUF2. So letters, an all letter text has become a text with mixed letters and numbers. And of course, if I set the machine to decipher mode and set the wheels back to the same positions, then I type in this mixed letters and numbers string and get back to the original hello. Now, I had no idea, I don't think anybody has any idea how the wheels were wired. So I just employed a random number generator to generate some wheel wirings for me. Unlike Enigma, where these days the Enigma rotor wirings are defined and published, and anybody can write an Enigma simulator based on that, I had to just create my own wiring. And I needed to be fairly sure that I was getting for a human language text in, that I was getting a reasonably randomized text out. So again, I have the index of coincidence. Because the alphabet coming out of the machine is now 35 characters rather than 26 characters, that means the index of coincidence for 35 characters is around 0.0286, and I'm getting roughly that when I throw in a bunch of plain text and I do the index coincidence on the randomized output. Now, a little problem with this system is that it's clearly been designed with a British or an American typewriter, and you only have the letters A to Z. And in encryption mode, you don't even have 2 of those. You don't have Q and you don't have V. And that's because Q and V, that's not so bad. That's because Polish doesn't actually use the letters Q and V, at least in native Polish text, although they would have to use it in foreign words. But let's not worry about that. Polish has 9 extra letters. So there's A with a little hook, ogonek, E with a gonek, L with a bar, C, N, O, S, and Z with acute accents, and Z with a dot. And although you can sometimes leave them out, it can make a difference having a word with this E with a hook in it. If it happens to be a verb in the first person singular, then you get an E with a hook. And if it's in the third person singular, you've lost the E with a hook. So it can be ambiguous if you don't have a system that has accents. And I have no idea how the user solved that problem. For example, if I wanted to write the Polish text, to jest ważna wiadomość, there's 3 words in there, and there's 3 accented letters in there. And I'm guessing that possibly they would add after an accented letter, the letter X. And the reason why I propose that is a possibility is that there is another language which has some Polish connection called Esperanto, which has a lot of accented letters. And there is this standard system for replacing the accented letters with the unaccented letter followed by the letter X. But that's just a theory of mine. Now, there were quite a few of these machines built, but the question now becomes, gdzie są LACIDA dziś? Where are the LACIDAs today? Now, I have been given this map by the Józef Piłsudski Institute in Hammersmith, which shows Polish evacuation from Warsaw as the Germans were overrunning Poland. They left a place called Piry on the 6th of September. They worked their way east and then south, eventually arriving at a place called Luck. It's written L-U-C-K, in Polish that is Luck. Then, and they arrived here around about 11th, 12th of September. They then went to a place here, Usiług, arriving 12th and 13th of September. This story of their escape is covered fairly well in Dermot Turing's book, The Real Story of How Enigma Was Broken, Prawdziwa historia złamania szyfru Enigma. And this book is also recently devenu disponible en langue française. Looking at a modern map, we now have Lutsk, L-U-T-S-K, on bottom right. And underneath it, you'll notice it's written in Cyrillic alphabet. You have the H22 road, which crosses the country and ends up in Ustuluch, which is also written in the Cyrillic alphabet. And that is because these places, which were in Poland at the time, are now actually in Ukraine. So finding them is a little more problematic than it would have been if they were in Poland. And the point is that a large hole was dug, and all of the machines that they tried to bring out with them, cyclometers, bombers, LACIDAs, were burned. And so there's a hole somewhere in Ukraine, close to the border with Poland, which may contain some very interesting things. And some colleagues of mine are making plans to go digging, but of course they have to get permission from the Ukrainian authorities these days. Now, some further studies that I'd be interested in working on. Does LACIDA exhibit the same cyclic properties as Enigma? In other words, can I create a cyclometer, or can someone create a cyclometer? And a feature of, this is also a feature of the Enigma's cyclic properties, that certain combinations of characters are known as females or samica. Do they occur in the use of the LACIDA? In other words, could we make a bomber to try and crack messages used on those? My research has been helped by 3 works by a gentleman called Christoph Guy. There's an article in Cryptologia, a well-known magazine of current publication. There's an Enigma Bulletin, which is published in Poland. And there's a fairly old book, fairly hard to find book, Szyfry Enigma, Metody Złamania, by the same gentleman, Christoph Guy. Now, I thought I would stop at this point and unshare myself and see if there are any questions. And probably the easiest way is to see if there's any questions, if you care to put them in the chat box. And I will then unmute you once I see questions. If there are no questions, then that's fine. Oh, here's Now, Martin, you've just asked a question.
Yeah. So did they use a repeated key? Did they send it twice? Do we know how they actually encrypted and sent the key across?
No.
That's easy.
Unfortunately not. There's no messages remaining as far as I know. And they'd have to be using this repeated key in order to get the same the doubly encrypted 3-letter thing to play with for a cyclometer or the bomber to work. But we don't know if they did that or not. So it would have to be a surmise, just like my wiring is a surmise that they did this and that it could be therefore cracked using that kind of methodology.
Okay. Can I ask one more while I'm on?
Yeah, sure.
I was just wondering why they did the 26-letter to 35-letter one. Do we know why they did that? Because it seems to me you had the extra keys, which were required, the extra letters required for Polish, and there's 9 of them. So instead of the 1 to 9, it would make more sense to me that you would use those extra letters for it. I guess maybe the typewriter they were using, but
well, they were using a British or American, I believe it was a Remington, in fact, or some such. So they were stuck with what they've got, although they could, of course, have redone the keys.
Yeah.
But I don't know. It's not, none of the amount of information available is very sparse. Christoph Guy, the person I referred to, has effectively written the same thing 3 times in 2 different languages.
Okay, thank you.
You're welcome. I guess there's no more questions. So why don't I go back into share mode, where I have my simulator. Now this is, Martin is well known to me as a creator of incredibly beautiful 3-dimensional simulations, but unfortunately this is a really basic 2-dimensional no graphic simulation. So I'm just going to set the keys to a preset value, and I'm just going to type in a message, and as I type you'll see the encryption in process. As a little amusement for myself, I've had it send Morse. The original machine would not have sent Morse. As messages were encrypted and typed, then Morse would have been sent by hand by somebody tearing off the paper and reading it and sending it. But I'm just, I like to add these features. So I'm just going to say, this is a message. Okay, so here we go. So we have T encrypted to O, and then H encrypted to V, and I encrypted to F, and S encrypted to Y. And I probably don't need to label this because you can see how that's worked. And then if I reset the wheels, switch to decipher mode, and then type in O, V, F, Y. And I've got the original word this back. Nothing really fancy there, but it's just proof that my simulation works and it gives the same answers in the 2 directions. So are there any more questions?
I'm sorry this isn't related directly to the talk, but you mentioned that the Polish intelligence was operating in 1941. Was that from the UK, from Britain then, or abroad?
Well, their immediate evacuation from Poland ended them up in France. And there's a rather fine book by a gentleman called Gustave Bertrand, which explains the entire story of what they were doing while they were working in France. Unfortunately, this book's only available in French, but
that's okay.
But yes, they moved to France, and then from France they moved to England.
Okay, thank you, and thank you very much for a great talk. Thank you.
Well, you're welcome.
I'm just thinking about the non-moving rotors.
Yes.
If you think of the Enigma and the plug board at the front,
yes,
you can think of that as being a non-rotating rotor.
Indeed.
And Turing's method on the bomber effectively makes it redundant. So when you were showing the figures about 150 million, of the plug board, it sort of doesn't matter.
Yeah.
With the fixed rotors on this machine, do you have a similar thing where it makes itself redundant, or have they known that and been clever enough to build it in such a way you still do have problems with it?
As far as I can tell, then the encryption, I mean, the encrypted wiring is just going through the 6 wheels in sequence. So I'm more inclined to think of that you actually need a 6-wheel bomb to do this, rather than being able to dismiss 3 of them by considering them to be a plug board.
Right.
That's my impression, anyway.
Yes, I mean that's why your 50,000 was it 50,000 times extra?
Yes.
Is important.
Mm.
Whereas in the case of the Enigma, your 150 million in a way isn't important because the method gets around it.
That's an interesting question. Who said that? Peter.
Yes, I wondered if they burnt all the machines, how did they test the strengths afterwards?
Well, that's an interesting point, isn't it? I guess some survived, is the rather lame answer I'm going to give, because they did give some to the British, and they may well have done that before they were destroyed, because they were using it for communications between Poland and Britain. And Martin Gillow has said, where's the cipher-decipher switch on your LACIDA diagram? How was it powered? Well, the machine itself was an electric typewriter, so I guess AC mains. And the cipher-decipher switch, I could probably go back to my presentation. So on this machine, the cipher-decipher and cipher-decipher switch is here, assuming you can see my mouse moving around. And it drives something unknown up here. But that is the actual switch. I hope that answers your question.
Jerry, the thing at the top that was rotating, was it just the decipher sign at the top? Is that all it was doing? So its actual operation is further down.
Yes, I guess that's true.
So
actually,
it just changes the label on the top.
Yes. I guess there's no pictures of it showing decipher. There's only pictures of it showing chiffre. But I guess that is the case, that all that's doing is rotating that. Yes. Yes. Yeah. Good point.
That would address what you were saying about the difficulty of accidentally using the wrong setting.
Mm.
You've got a big sign at the front, it shouts at you.
Yes, it makes it less likely, doesn't it? Somebody asked a little earlier, why the different number of connections on different wheels? Not known is the answer to that one. Not explained in any of the documentation I've found. They just wanted to be different, and it is very different from all the other machines.
Is it fair to say that it was never broken by the enemy of the Poles?
As far as
they broke it themselves, but nobody else did. Is that fair to say? Well,
I don't think they used it very much anyway. And as far as there's no German records that, or any other records saying that they broke it. But I think once Rejewski and co cracked it so quickly, they probably decided not to use it anyway. And I don't see anybody putting any more comments up. Then I guess that's the end of the talk. I'd like to thank you for attending.
Thank you very much, Jerry. Thank you.
You're welcome.
Yes, thank you.
Thank you. Very interesting talk.
Yeah, thank you very much indeed. Excellent.
Yeah, thank you very much.
Thanks.